Okay, um, I'm going to start today's lecture with a question, and I'm going to get myself spinning with these weights in my hands here like this. I'm going to give myself probably 3 pushes with my legs, and my question is, what will happen as I bring these weights in after I'm spinning? So go ahead and think about it and make a prediction. What will happen to my speed? All right, so I'll go ahead and give myself a few pushes here. Once I start spinning, I'll bring the weights in. Okay. All right, now I'll do the opposite. So this time I will start with the weights out, in, and then I will bring the weights out. So I'll give myself about 3 pushes again, and then push the weights out. All right. And one last time, just a combination of both. I'll start in, or start out, sorry. Get going a little faster. Whoa. All right. Okay. Okay, before I answer the question about why I was spinning faster or slower in the chair, let's go ahead and learn about a new quantity called angular momentum. Angular momentum is represented by the symbol L. Let's go ahead and write that down. And L, just like P is a vector, but if we remember P, and this is capital L, by the way, lowercase p is equal to m times v, right? And this was for regular momentum. For angular momentum, we have L is equal to I, capital I, times omega. And omega is a W, maybe like a script W. And this is a vector. So you can see that the formula for angular momentum is similar to the formula for linear momentum. All right, so before we talk about what this formula means, how to use it, and answer our question, let's just go through one part of this at a time, right? We have 2 quantities here. We have, or 3 new ones, right? We have angular momentum. We have something called moment of inertia, which kind of sounds like a moment in time, but it actually, the moment stands for momentum. So moment of inertia, so the momentum of inertia. And then finally, angular velocity. So let's talk about both of these to get an idea of what angular momentum is. So we'll start with angular velocity. Angular velocity is omega, and omega is equal to the change in the angle divided by time. And so just like we have regular velocity being the change in position divided by time, here we have the change in angular position divided by time. And although we usually like to use degrees, this is actually going to be in radians. And units for time will be in seconds. So this quantity right here is the change in angular position. All right. So okay. So let's talk about how to use this, maybe with an example. And this is one that we talked about before with circular motion, I believe. I mentioned it in class. Let's say we have a merry-go-round. And you're riding on it, and there is a axis of rotation at its center. You decide to ride on it because you're braver at the edge of it, and your sibling decides to ride on it closer to the center. Now you're both going to go around the circle. Let's say you're sitting near each other like this. You're both going to take the same time to go once around, right? And we'll say that that time period is equal to 3.5 seconds. And so we'll say t equals 3.5 seconds to complete one revolution, to go around once. Now in physics, the time to complete a cycle is also called a period, which is represented by capital T. And I'll come back to that later in the year when we talk about waves. All right, so the time to go around once is 3.5 seconds. And we'll say you're sitting, I don't know, just make up a distance here. We'll say you're sitting 3 meters from the center. So we'll call that R, while your sibling is sitting 1 meter from the center. And even though you're sitting farther out, your time to go around once is the same as your sibling, right? You're sitting right there, right next to them. You're going to go around together just like this. And the time to go around once is the same regardless. You can also think of that is that you complete 360 degrees in the same amount in 3.5 seconds, just like your sibling does. You both complete 360 degrees. Now, we might remember from math class that 360 degrees is the same as 2 pi radians. It's just another way of thinking about angles, right? Instead of calling them degrees, we call them radians. Now, what does that mean? 2 pi is approximately 6.28. So 6.28 radians is equal approximately to 360 degrees. So what the heck is a radian? Well, if we divide 360 by 6.28, we can see that 1 radian is approximately 57 degrees. So I'm just going to write that down. That's kind of a neat thing to know, right? 1 radian is approximately 57.3 degrees. All right, so that's all a radian is, right? When we say a radian is 57.3 degrees, once around is 6.28 radians. So that kind of makes sense. All right, so we're saying then that your angular velocities are the same, right? We can go ahead and write that down. For you or your sibling, your angular velocity is equal to the change in angular position divided by time. This has to be in radians, so 6.28 radians, or rad, divided by 3.5 seconds. So we do the math there, 6.28 divided by 3.5 gives us about 1.79 radians per second. Okay, that says per 1 second. Okay, and that's our angular velocity. Now the question is, what about linear velocity, right? Because I really want to talk about angular velocity, but I just want to show you that while these two objects have the same angular velocity, their linear velocity is different, right? Because the linear velocity is about distance, right? We could say that v equals d over t. But you're going to travel a different distance. You're going to travel a longer distance than your sibling here. Why do we know that? Because you're sitting a different radius away, right? And the radius is going to be the distance. So for your sibling, I'll say v sib is equal to, what's the distance around a circle? It's the circumference, right? So that's going to be equal to 2 pi r. So we can say that that is 2 pi r divided by t, and then for you, it is also going to be 2 pi r, but you're going to have a different r, right? So I'll call this r1 and this r2. Okay, divided by the same t. All right, so let's go ahead and plug some numbers in really quick. So we'll see that v sib is equal to 2 pi times, I think your sibling was 1 meter away, time 3.5 seconds. You were sitting 3 meters away, same time, 3.5 seconds. And we can go ahead and see that the velocity of your sibling, if we plug that in our calculator, is equal to 1.81 meters per second, where the velocity of you is equal to 5.39 meters per second. So you're traveling much faster. And actually the velocity of your sibling is, since they're only sitting 1 meter away, is the same as the angular velocity. I think, I bet if we redid that calculation, I think you're not exactly sweeping out 6.28 radians, right? You're sweeping out 2 pi radians. So I bet if I go back and use 2 pi divided by, whoops, let me go ahead and put that in together, maybe use my parenthesis, because sometimes that matters. 2 pi, I don't think it should here though. 2 pi divided by 3.5 is going to equal, oh, I guess that is the same, 1.79. All right, so I guess that this should be 1.79 over here. I'm not quite sure where I got the 1.81 from when I did that earlier. Okay, so yeah, that shows a couple things. So angular velocity isn't the same as linear velocity, right? You have a different linear velocity. You are much braver sitting out at the end. You're traveling a further distance in 3.5 seconds than they are going in 3.5 seconds. So they are traveling slower sitting in by the middle. And then furthermore, you both have the same angular velocity, because you both, around this axis of rotation, you both take 3.5 seconds to complete one revolution around the axis of rotation. So same angular velocity. Okay, let's go ahead, before we talk about the next quantity, which was I, or moment of inertia, let's go ahead and take a short quiz. All right, so the quiz is going to look like this. I'm going to ask 3 questions, and I want you to go ahead and answer A or B, and then make a prediction, and then we'll go ahead and test them. And this will all have to deal with moment of inertia. So let's say that we have 2 equal mass meter sticks, so 2 meter sticks from the classroom, and we're going to spin 1 meter stick about its the axis of rotation. Where we spin it is going to be its center of mass. This symbol right here is the symbol for center of mass. You can see I drew that twice. All right, so we got 2 identical meter sticks. One time we're going to spin it about its middle, and the other time we're going to spin it about its end. So maybe we hold it right here at 50 centimeters and try and spin it this way, right? And then we hold it at its end and try and spin it like this. Which one do you think is easier to spin? Easier to accelerate? All right, go ahead and take a guess. All right, write that down somewhere. All right, let's go ahead and go to the next one. Now we're going to attach masses. And even though we're going to attach masses, we're going to keep both meter sticks the same mass, right? And what I mean by that is this meter stick's going to have m plus the mass of the meter stick. This meter stick's going to have m plus the mass of the meter stick. However, in the first case, the masses are going to be out at the ends while we're going to spin at 50 centimeters. And in the second case, the masses are going to be closer in, very close to the axis of rotation, maybe at 48 centimeters and 52 centimeters, and then spin again about its center of mass. So go ahead and take a guess there. Which one's feels easier to spin, is easier to have an angular acceleration? A or B? All right, let's move on to the final one. And then we're going to do the same exact thing we did a second ago, but this time we are going to have 1 meter stick with just with one mass at each end, and the next one with two masses at each end. So this meter stick will be heavier, meter stick B this time, than meter stick A because of the additional mass at each end. Which one will be easier to spin now? Once again, spinning about its center of mass right here, where the axis of rotation symbol is drawn. And go ahead and take your guess there, A or B. All right, so let's go ahead and try it. Okay, try and set this camera. Jeez. All right, so we're gonna start off by spinning just the meter stick about its center of mass, which is at 50 centimeters, and we'll put the axis of rotation right at 50. So I'll hold it right here and spin it. Fairly easy to spin. I'll then move the axis of rotation to its end and spin from here. So definitely tougher. Okay, let's go ahead now and increase the mass of the meter stick. I got two different meter sticks here. One with two tennis balls taped right in the center, at the center of mass or close to it. And the other one with a tennis ball taped at each end. And so we'll go ahead and spin these now. So we'll start with two tennis balls at the center. All right, turning fairly easily. Similar to the one I did before about its center. Now let's go ahead and put a tennis ball at each end. Go ahead and hold it at 50. Axis of rotation still at 50. All right, still spins, but definitely tougher. Not as easy. And that was two objects with the exact same mass, but definitely way easier to spin this one, right, than it was this one right here. All right, now what if we increase the mass, right, and go to maybe two tennis balls at each end? So this will be the heaviest one yet, right, because now we have four tennis balls and the meter stick. I'll go ahead and hold it at 50 and turn it, and definitely the toughest for me to accelerate or to speed up with an angular velocity. All right. So what we saw there with moment of inertia, which is what we're talking about, or what we saw there with mass, I guess is a better way to say it, is that the mass being different distances away and being larger gave us, made it harder to rotate, right? So I think the two things we can say there is it was harder to rotate. These would be our conclusions from that quiz or the demo. It was harder to rotate when the mass was farther away. Farther or further? I'm going to go with farther. Farther away from the axis of rotation. Whoops. And we also saw that when there was more mass, it was harder to rotate. Okay, so more mass and the mass being farther away from the axis of rotation made it more difficult to rotate. So moment of inertia is what we're talking about here, right? So our formula for the moment of inertia of an object depends on its mass and its distance from the axis of rotation. So it depends on two things. Now, at its simplest, for a tennis ball, say a distance away from an axis rotation, a particle mass, right? This is a mass that has all of it, or an object that has all of its mass at one point, a particle mass. Its moment of inertia formula is mr squared, where m is the mass of the particle, and r is the distance from the axis of rotation. Whoops. This is not, that says from, distance from the axis of rotation. This is not the radius. All right, don't tell me that this is the radius. I know it's r, but it's the distance from the axis of rotation. All right, now, this is for a particle mass, right? So when all the mass is located at one point, Now, we know an object like this does not have all of its mass at one point. And that's what we consider with the idea of a center of mass, right? But that's not good enough for moment of inertia. When we're talking about moment of inertia, we consider something an extended object. So something like a meter stick has an infinite number of masses. If I'm rotating right here, has an infinite number of masses at some distance away from the axis of rotation, right? I could sit here all day and draw different distances for each atom of the meter stick. And so what we need to do is add up all of those MR squares. We need to integrate all of those MR squares and collect them into one formula for I of the meter stick. So that actually requires calculus. And since we don't know that, what we do is we are just given that formula in algebra-based physics. But we can make a prediction about the formulas, right? Because they're different based on if the axis of rotation is right here or if the axis of rotation is right here. Because when an object has more of its mass further, right, when r is larger, when it has more of its mass further away from the axis of rotation, that I would be what? Right? So let's think about that. So what I'm saying is, if I come down here, in this case, I have the center of mass right here, right? I guess it doesn't really matter. I'm going to draw it anyways. But let's just look at where these particles are. Here's the axis of rotation right here. Here's the axis of rotation right here. So in one case, my axis of rotation is right in the center. Are most of the distances further or closer to the axis of rotation? Then what about down here? Are most of the atoms further or closer to the axis of rotation? And you would say, well, down here it seems like this side of the meter stick, these are much further away from this axis of rotation. And wasn't this the one that was harder to rotate too? So which one of these would have the larger I value? Well, you would say this one, right? And that turns out to be correct. The formula for I here, which requires calculus to get, but you can go ahead and just write this down, about when the axis is at the center of mass, is 1/12 the mass of the meter stick times the length of the meter stick squared. And when the axis of rotation is at the end of a meter stick, and the center of mass is right here at its center because it's a symmetrical object, I is actually equal to 1/3 ml squared. And is this larger than this? Yeah, because the fraction 1/3 is definitely larger than 1/12. All right, so the larger I value is tougher to rotate. So something that would have a larger I value, let me see if I can write this down somewhere. Just running out of room. A larger I has a greater mass or a further distance from the axis of rotation. Which was R, right? Okay, so what we're saying then is I is larger when M or R are greater. But obviously, which one's going to matter more? What if I doubled the mass and doubled the distance from the axis of rotation? Which one would have a larger effect? You should say the distance from the axis of rotation because of the squaring effect, right? I is proportional to M, but I is proportional to r squared as well. So anyways, let's go ahead then and solve the problem we started initially with, right? Which was, why was I speeding up in the chair now? Okay, so let's go back to angular momentum. Now that we understand what this formula means, I'm going to go ahead and write it out really quick. So we have angular momentum, just write it one more time, is equal to the moment of inertia so there's no, yeah, okay, times the angular velocity. All right, well, why does this matter? Or why is this going to help us? Because there is something, just like we said before, you should notice a trend here. PI equals PF, right? MVI equals MVF. We said EI equals EF. These conservation laws are super important in physics and how our universe works. And so we're going to add another one, right? And so we'll have Li equals Lf. And angular momentum is conserved. So that means that we can go ahead and rewrite this formula. Initial times omega initial is equal to I final times omega final. Now you might say, well, why are these different and why is this going to help us? Because if we look back up before, PI equals PF, when you have a collision like this, right, and PI equals PF, the mass doesn't change, right? The velocity can change, but the mass doesn't, right? And here, this is different now. Notice why, right? Moment of inertia can change, can it? Right? Because let's think about this. I was sitting on the chair, and I think initially I had the masses out. So the mass was out towards the end, right? I was holding the weights out at the end. What was the moment of inertia? Was it larger or smaller when I held the masses out? And you should be saying what? Larger, right? And then I got myself spinning, and then I brought the masses in. And even though I didn't change the mass, what did I change? What did I change there? You should be saying, well, I equals mr squared, right? So what changed? Well, the mass didn't change, but r changed. The distance from the axis of rotation changed. So I made I smaller. Now, because angular momentum is conserved, when I made this smaller, in order for angular momentum to be conserved, what had to change, right? Well, let's say this side is equal to 100. I'm just making some arbitrary number, right? I don't know what it really is. This side also has to be 100. And if you bring the masses in and make this number smaller, then you're going to need a larger number right here to make up for it. So omega F had to become larger from whatever it was initially, right? This was definitely smaller then. So I sped up. And the opposite was true when we went the other way, right? When we started the other way, just write it one more time. In the other case, right, I think I started with the masses in, right? And so I started with a small moment of inertia. I got myself spinning, so this was larger. And then I made this large, right? So when I made this larger, this had to get smaller. And I slowed down, right? And so you saw the opposite being true. But once again, this side had to be whatever it started with. If it started out at 75, then this side had to stay at 75, assuming I didn't lose any energy due to friction or anything like that. There's no torque causing me to slow down. But yeah, angular momentum is conserved. So that is why it was the conservation of angular momentum. All right, so learn about a new conservation law. We had momentum, we had energy, now we have angular momentum. Can you think of an example of where this might show up in reality? Outside of the classroom is what I mean. And you might say a diver or a gymnast or something along those lines, pulling their legs in to do a tuck. You could say a skater, a figure skater, bringing their arms in to spin faster. And you see examples of this. So they aren't getting free energy, right? There's nothing free. What they're using is the conservation of angular momentum. They're changing their moment of inertia. They're making it smaller to speed up their rotation. We also learned about moment of inertia as understanding that the mass, where the mass is located, does affect the object. And we call this an extended object when we talk about objects this way. Because you might say, well, why didn't we do this all year, right? And it's easier to think of most objects as a particle mass, as one point, that all their mass is acting from one point. And that's actually what we do with things like with their center of mass. But when we want a more realistic idea of the mass, it does matter where it's located. But the center of mass is still a useful idea. But this is a particle theory, and we use an extended object theory to solve this. So anyways, hopefully that makes sense, and have a good rest of your day.